Hello there, and welcome to a top-down approach to sheet metal design. My name is Dave Bazinet, and this is a recording of the presentation I gave at our 2013 user group event. So a little about myself before we begin. I'm an AE over here at CAD I've been using the software roughly 13 or so years, around the 99-2000 time frame. And being at CAD I've gotten certifications covering the entire product line. So everything from SolidWorks to Composer, simulation, PDM, etc., etc. So prior to my life in CAD I was actually in industry for, call it roughly 13 years. I have a sheet metal machine design background, and within that time in industry, I spent it doing everything from working on the shop floor through designing product. So this session, what's the goal of it? We're going to see how easy sheet metal parts are created within an assembly or using in-context design. We're going to see what happens when design changes are made and how that affects the parts. And then we're going to see how the costing module can play and help us determine what our part will be and use that as a guide to help design. So the agenda, we're quickly going to review in-context design, sheet metal, and costing, all three of those modules. We're going to put it all together. So like I just mentioned, we're going to take, in this case, a grill assembly. We're going to design a sheet metal skirt cover using the grill as a frame. And we're going to use the costing module to help us determine our cost and keep it within the design parameters. So after we go through that, we're going to see what's new in 2014 briefly with regards to sheet metal and costing. And then we're going to wrap things up. So in-context design, what is it? When we're building our assembly models, there's a couple methods to do it. There's the bottom-up and the top-down approach. So the easiest way to explain it is the bottom-up is that we have all our parts and we put the assembly together. So if I go buy something from IKEA, I have to take all those components and build that final assembly, or say bookcase, for example. That would be bottom-up assembly modeling. Top-down modeling is the exact opposite of that, where I have a frame and I want to build parts to fit within that frame. Using that frame as a guide, that helps me design around my parts. So that would be top-down modeling. So the benefits of top-down is the design work is done within the assembly. So as I'm building my parts, I know they're going to fit within my assembly. I don't have to worry about, well, if I make this part this size, will it fit in here? What are my constraints, etc. The other good benefit is that if that geometry updates, my new parts are updated as well, depending on how they are constrained. I'll put that one little asterisk in there. And of course, the parts, if they're designed in context, they can be broken out and saved later on, separate from the assembly. There's one thing to note on this. If you have a part that's designed in context and it's going to be used in other assemblies, that's generally a bad idea. Reason is, if I have a part that's designed in context of one assembly and I put it into another assembly, if that second assembly updates, my original part is not going to update with it. And that's because that part is based off the first assembly, not the second assembly. So it's kind of you gotta use some discretion if you're making them in context versus using a bottom-up method. So we're going to talk again briefly about sheet metal, and that's because that's the main focus of this session, creating sheet metal parts within the assembly. So some things to think about first are what defines a sheet metal part, some methods to create the parts, features available, and then we'll just discuss flat patterns briefly. So what defines a sheet metal part? So first, just because it says sheet metal doesn't mean it has to be sheet metal. This can apply to paper, cardboard, anything that you bend up and you would need a flat pattern of. So in other words, to use the quote unquote sheet metal functionality, there's two rules that you have to follow all the time. If you don't follow these two rules, you won't be able to use the functionality, or it won't be considered a sheet metal part. The first is that the part has to have a uniform thickness throughout it. You can't have a bottom piece, for example, or a bottom face be one thickness and a sidewall be a second thickness. It has to be the same thickness throughout the part. The other rule is that it must contain rounded edges. Okay? So I can, depending on the method I use to create the part, this may or may not be the case, but in the end, to use the sheet metal functionality, I need to have rounded edges. So again, if I have a box, the bottom corners have to be rounded in the end. Now, when I have a sheet metal part, there's two features in my tree that I will need. I cannot get rid of them, and I can't have one without the other. First one's the sheet metal one, in this case, feature. Of course, you can always rename these after the fact. The sheet metal feature contains the thickness, bend radius, bend calculation information, all that. The other feature is the flat pattern feature. So as it indicates, it contains all the flat pattern information. This also controls if the model's bent or folded as well. And that's just by suppressing or unsuppressing that feature. So creating sheet metal parts, there's a couple methods you can do to create them. The flange method and the convert method. So with the flange method, you see here, we have a sketch, comes up over, etc. We extrude it out using a sheet metal base flange feature, and then we just add features on our flanges on top of that. So in other words, I'm building it up as I go along. That's the method most people are familiar with. The other method we have is the converting method. And that's where we take a solid model and we convert it to sheet metal. So using that, if you see here, these flanges, with the exception of the bottom, which you can see there, are converted to sheet metal. The bottom is left open, in other words, in this case. And then we can get our flat pattern here. So again, depending on how complex your part is and which method is easier to use, again, it all depends on what the part looks like in the end. So some sheet metal features. Obviously, we have base and end flanges. And flanges you can see here, here on the bottom. A base flange will be typically your first feature if you're using the flange method. Actually, it will be the first feature. We have gauge and bend tables. We can control our part with tables as well. Miter flanges, we have corner trim, sketch bends, jog hems, lofts, fold and unfold. So for example, right over here, I would have unfolded here in that flange, put the cut in, and then fold it back up. Actually goes across the bend. Say for example, if I had fixed tooling, that cutout could only be a certain size. We have closed corners to help us knead up or clean up our corners, corner breaks, form tools, tabs and patterning, multi-body techniques. There's a lot we have with the sheet metal, and it just keeps getting better and better over the years, adding more functionality, etc. So talk about flat patterns real quick. So flat patterns, if you're costing out a part, they're typically valuable. I'll say that, only because when we get to the SolidWorks side of things, you'll see how it varies with it. But flat patterns, we can see what our flats look like, where our bend lines are, center points on our form tools, etc. So we can save them right from a drawing, or we can export them directly from SolidWorks. And usually if we do that, we save it as a DXF and then bring it into our nesting software or whatever else we're using. So I say they're essential for costing out a part because you get the actual flat size. And if you're adding scrap onto there, you typically need to know what that flat pattern length would be. All right. So we'll talk about costing real quick again. So what is, why use it, how does it work, and then SolidWorks costing versus hand calculations. So what is, why use costing? So it's essentially a module within SolidWorks that helps give you an estimate of what your part will cost based on templates that you have. So again, why use it? A couple clicks of a button, you can get an estimate of what your part costs. That speaks for itself right there. Helps you not over design the part when you don't need to. It's a lot easier to use than traditional methods. So in other words, calculator, we're using spreadsheets, whatever you have. And it's always based off the same data. In other words, templates, like we have in SolidWorks. Which brings me to here. So it's driven by templates. What that means is the data remains consistent, nothing changes. We do have the option to put in overrides as well. So much like your SolidWorks templates, it'll give you a good beginning. If you need to modify something after the fact, we can do that. We also have multiple templates for different scenarios. So if we have machine parts, we can have a template for that. If we have sheet metal parts, we can have a template for that. We can have templates for internal, external vendors, whatever we want a template for. Again, just like SolidWorks. So we can add discounts or markups, and we have an ability to create a baseline cost. So in other words, we can run through different design scenarios, like we're going to see later on today, using a baseline cost. And finally, in the end, we can actually report it out and have a report of the cost, all the operations, all the data we need to cost out the part. So SolidWorks versus hand calculations. The one on the right is typically, or is a cost spreadsheet I used before. It was a template I created. It was all pull down menus that I had to pick from. And I still had to input the quantity, the size of items, any operation I had to add into there, etc. The one on the left is SolidWorks. It's contained right within SolidWorks. I just pick the template I want, pick my steel, for example, gauge, etc. And then I just click calculate, and it automatically calculates for me. It automatically figures out what operations are involved, what size, the flat pattern, all of that information. It automatically figures it out for me. All right, so I mean, that pretty much speaks to itself right there, which is going to be a faster method. Obviously, the software is going to be faster. Anytime I can use the software to take care of an operation for me, I'm going to use it. So we're going to put it all together now, essentially. So again, like we mentioned earlier, we're going to create a skirt to surround the existing grill that we have. We're going to avoid interference with existing features. So again, using that in-context design, we can design around the assembly. After we have our design created, we're going to cost it out. So we want to try and keep the cost around $50 for the skirt. Again, quote unquote, this is make-believe. Obviously, $50 for that, I'll tell you right up front, no problem. But in this case, we're going to kind of exaggerate things a little bit just to show you. And then right off the bat, we're just going to create a baseline cost. Because, right in red there, once we get the first design done, it's always done right away. It's always done the first shot. No one ever comes back with design changes or requests or anything like that. And that was a little joke there, so. All right, so having said that, let's go ahead into SolidWorks, and I opened up the assembly already. So this is what we have. if we take a look at it, our grill, and like you can see in the PowerPoint there, just pop back up to it real quick. We're going to create this yellow grill skirt cover right here. Pretty basic shape, full flanges on it. We're going to add some holes later, and then show how we can put those holes from the assembly level down to the part level. All right, so let's go ahead and get started. Get in SolidWorks. I'm in my assembly right now. All right, and the first thing I'm going to do is put in a new part. So insert component, new part. Now if I look down here in the bottom left corner, select the face or plane to which to position the new part. In other words, I'm going to create a part which is virtual within this assembly. So the first thing I have to do is pick a face where I want to sketch on, or start my sketch on. If I look at it from the side, this front member here extends past the part. That's what I want to do because my skirt is going to surround it like so. So I'm just going to click on that face, and you notice here my part is now blue, and it's showing me that it's virtual with a little caret there. All right, so I'm automatically in sketch mode. Go to normal to the face. You can see I'm in sketch mode. So I'm simply just going to draw a rectangle like so. All right. Now if I look at it from the side, you can see that sketch is drawn right on that face of this member here. Okay. So I'm going to come in, and just like I'm in regular standard SolidWorks, I'm going to start adding relations. I'm going to make that collinear. Here I'm going to make collinear. I'm going to do the same thing down here in the corner. So from here to here, collinear, and to the top, collinear. So what this is doing is tying this sketch line to the top or to this edge of the shelf. So if this shelf height ever adjusts, my front skirt is going to adjust with it. So now that I have my sketch, I'm going to go to my sheet metal and base flange. I'm going to kind of rotate my model a little, make sure I'm going in the right direction. And bump this up a little bit. And let's make it 3 millimeters. So we'll make it 11 gauge. Nice heavy duty skirt. Again, like I said earlier, it's all exaggerated. Obviously, if you're doing just a cosmetic cover, you're not going to make it out of 11 gauge steel. All right, so 3 millimeters. I reverse the direction so it's coming out of the part. And then I'm just going to hit OK. So now if we look down here, base flange, and you see that little arrow? That means it's within context of something. So in other words, it's in context of this assembly. All right. And then once we get some more features in, I'll actually open up the part just to show you what's going on with that part. We have our first flange done, or our first feature done. I go ahead, go up to edge flange now. And I'm just going to click on this edge and drag it down. I'm not going to be concerned with the length right now. You'll see why in a minute. Move over a little more, and I'm just going to pick that edge. And the other thing, I'm not concerned with which edge of this part I pick. It could be either or. It doesn't matter. Now, the reason it doesn't matter is because I'm dragging it in this direction. So in other words, from front to back. Now, if I zoom up here and zoom in, notice how the material is going with inside the part right now, or that assembly. I have all these options I can change as well. In other words, material inside, material outside, or the bend outside. I'll just put material outside. And in this case, I want to go, instead of a blind distance, I want to go up to a vertex. I'm going to come down, and I'm just going to try and find a vertex somewhere. So blind up to vertex, and try and pick one. Say that point there. Okay. Look good. Or at the same time, say we wanted to come right up to this point right here. Can always clear it and attempt to pick this point right there. All right, so it fits right in there. So ultimately, in the end, I have these side flanges. I want to put a return flange here on this side. Same on the other side. On the bottom right here, I want a return flange coming in. And up front, I'm just going to have a return flange coming in and down afterwards. All right. So I'm just going to hit OK here. All right. Here's what we have so far. And you notice I put those two flanges in by myself. All within command. All right. So let's go ahead and add those return flanges. In this case, I'll just hit section view. And so I can see the back. All right, so here's what I have. Now you notice this flange goes all the way to the top, but I want my flange to begin down here. So I'm just going to rotate it so I can see it. I go to edge flange again. I'm going to pick the edge. And I'll just drag it in. Again, I'm not concerned with the length of it for now because I'm going to actually give it a distance. I'll pick that edge. Now I need to modify both edges, or both profiles. So I'm going to click on the first one, edit flange profile. And you notice the sketch is black right here. Well, when we see the black, we automatically think it's fully defined. In this case, it's not. I can actually click on this and drag it down, and that'll turn it blue. Just like so. All right. Oop, I'm going to go to front view. Go into dimension, and let's pick a dimension. Say from the top of the shelf to here, we wanted 55 millimeters. And same thing too with this profile, this flange here. We can actually give it a length or a depth. The second we do that, let me hit back for a second. Notice we have blind and we have up to vertex. All right. I'm going to edit it. And let's do this. Let's pick this edge here, make them collinear. So now it's fully defined right there. My bottom half is fully defined as well. All right, I'm going to hit back. I'm going to click on the second profile now. Again, you see the line is black here, so we think it's fully defined, but we can drag it off. So while that one's highlighted, I'm going to pick over here again. First thing I'm going to do is make U2 collinear. And then I'll just add that dimension in again. Then I know that's 55. Time you could add relations depending on where they are in the tree and if the sketch is shown, etc. So if you go view and sketches is on, all right, we could hide and see it over there depending on the order in which they're at. All right, and then I'm going to rotate it again so I can see which way my material is going. So you can see with the preview here, the material is outside, put material inside. I'm going to hit OK. And you notice it gave me a little rectangular relief here. You can always come in after edit the feature, and you can change a relief type for that one option or for that one flange. So there's my tear. Or you can set it globally across the entire part. In this case, I'm just going to modify the ones that I see fit. Rectangular relief there may not matter at all. It may be perfectly fine. Now if I rotate it over, here's what we have so far. Zoom out and then zoom back in. So you can see how we're designing the skirt using the existing geometry to design around. All right, so that's the back flange. The bottom here, we're going to do the same thing. Edge flange here, we're going to drag it in. Again, length I don't care about, but I can drag it however I want. Let's try to here. I'm going to edit the profile again because I want to avoid this one right here. So I'm going to drag it. All right. Come in, give it a dimension. There we go. Try this again. Make sure I can grab the right entities. And I'll make at 1 millimeter inside to inside. There we go. All right, and of course we can take this edge right here, take that edge, make them collinear. Not worried about my flange length. I'm just making sure they all match up. And we can see the materials on top of it. So we can hit OK. And that's what we have there. All right, and again, this is all just using this assembly as a guide to help us create it. And then finally we have the top here. So edge flange. Again, just the same steps we went through already. Oh. As long as I add it, let's do that again. Here to here, click on you. Drag you in, drag you in. And this time what I'm going to do, I'm going to pick this flange, pick that edge, make them collinear. I'm going to pick this edge. I'm going to pick this edge. So you can see it a little better. Make them collinear. And then pick you, and you, make you collinear. Hit back, so I can see where my material's going. In this case, that's fine. So I'll hit OK. See now how we get that nice flat or flush top here. And then I'll add one more edge flange. Pick that edge, drag it down a little. Look at it from here. In this case, I'll just give it a blind distance of 50. I really don't care what the length is or if it lines up to anything. I just want to make sure it's 50 in the end. And then just make sure that the material is facing the right way. So there's our skirt. I open this up. Let me get out of edit part first. If I open up my skirt, here's what I get. All right. And of course, that bend may be a little tricky depending on your tooling, but in this case, it works. There's the rectangular release that I have by default versus my tear here. And you notice in here, we have those external references. To find them, I can always right click up here on top of my tree and list external refs. And it will tell me what I have. All right. So in the end, we could always break them as well, but in this case, we're going to leave them for now. All right. Let me go ahead and close this. All right, so we have our part. I want to add some mounting holes in here. Okay. Let's go ahead and do that. Let me go ahead, put a section view. So I'm going to work in the back first, just to make it a little easier. All right, I'm going to zoom in. And simply a matter of just using the hole wizard. That's all it really is. Let me edit this part first. Hole wizard. And in this case, we'll go with some countersunk holes. Well, maybe we'll just go with the regular hole. All right. And I'll make it a 1/4 inch hole. And just through all. So positioning it, I'll just click a bunch of holes here. And actually, you know what? I'm just going to do this. Place one, and that's all. I'll come in, dimension it, and make that 6, 10. Then from the edge, 10. Hit OK. And OK. And you notice how it didn't go all the way through. All right. If I come in, open up the part, my hole is here. It is in my part. Okay. So let me go back to the assembly again. Let me delete that. And then I'm going to get out of edit part mode. I'm going to go to my assembly feature and use hole wizard. And in this case, I have a hole. It's a 1/4 inch hole through all. So same things we had earlier. Same settings. Nothing's changed. I'm just using the hole wizard up at the assembly level versus at the part level. Move that out of the way first. All right. I'm going to hit OK. Oop. Make that 10. Rebuild. All right, so now you can see the hole goes through our entire part. That's just one thing to keep in mind with when you're adding holes using in-context design. Do you want it to apply to all the parts or just to the single part? Now here's the beauty. If I open up this part, I don't get the hole. It's not there. That's because it's at the assembly level. All right, and not the part level. If I come in and edit the feature, come down here, I have this option to propagate features to parts. I'm going to check it. And then in here, I'm just going to delete that. So it's just this one part. I'm going to hit OK. So you see by taking out the leg, it doesn't apply to leg anymore. If I open up the part, there's my hole. Let me go back in. to feature. On my bodies, I'm going to just select all. And now you see the hole right through there again. All right. And you can see here, if I collapse the tree, we have a hole that is separate from the part. So again, it depends on the situation, what you're doing with the hardware, where you need those holes if you want them in there. Okay, so you can see adding holes into our parts within the assembly, no problem. We also have other features as well that we can use. We can put in a hole series. So if you want to add hardware along with the cutout, we could. We could do simple holes, extruded cuts, revolve cuts, fillets, chamfers, weld beads, patterns, as well as a belt and chain. So if we're using gears, we can put that belt profile in there. All right, so I'm going to skip adding all these other holes for now because the process is the same as before. Instead, let's focus on what our part costs right off the bat, or it's the next part of this. So I'm going to go ahead and open up the part. And then we're going to open up the costing module. All right, tools and costing to get to it. In this case, it's already open right here, and it'll be the last icon in your tree. So what I'm going to do is pick the material. So in this case, steel, plain carbon steel. And again, these are all set up by your templates. So if I launch a template editor, first off, just to show you, general materials in here, thicknesses, my operations, so cutting, bending, library features, any custom operations as well are in here. But to add it is simply just pull down menus, and that just adds it like so. So you just repeat that for every material thickness that you need out there. But in our case, we're assuming our template's already set up. So I'm going to go ahead and pick plain carbon steel. My thickness is automatically going to pull in from the part file. All right, and if I change the thickness in here, I always get a little reminder down here what my part model thickness is. Material costs we're going to leave alone at the default because that's pulling from the template as well. And what am I going to cost? The bounding box, the flat pattern area, custom size, what have I. Any offset material I want to put in, I can do. I can preview it in the graphics area as well. So give me that little bounding box, depending on the offset. I can add scrap rate in here. So if I know I get 2% scrap off of my flat, I can add that in, and that'll help calculate the actual cost. Or an estimated cost, I should say, because cost is always changing, whether it's scrap rate or labor hours, etc. The final thing is the number of parts and the lot size. And then if we wanted to add a markup or a discount as well. So it's going to calculate the cost based on those parameters, and we can see it's already at $77. So material alone is 86% of our cost. Okay, manufacturing it is only 14%. So if I look at my tree over here, expand that over a little bit, I'll actually get a breakdown of the cost. So there's 7 bends, so 1, 2, 3, 4, 5, 6, 7 on the bottom. The cut paths, it's these here, okay, as well as the setups, so laser and bending. So it'll break all that out for us as we go along. All right, so we created a baseline, or we costed out our skirt. We want to create a baseline cost now for this, because I want to try and keep this down to $50, okay? So I'm just going to go in, and this little lock here, I'm just going to click on it. So it's setting up a baseline cost. It's actually going to go through and create the flat pattern, etc., for us to play with. So if you remember back in our PowerPoint, our main focus is to keep this skirt around $50. Okay, so to do that, we're going to have to make some changes to our design, obviously. So that's why I created that baseline cost up front, just so I have what it originally was and to compare it to what changes we're going to make. So we're going to make the design change now. We're going to try and lower the cost even further from the $76. So we're going to change the material gauge, we're going to update the cost, we're going to compare it, and then we're going to make some other changes as well. All right. So let's go ahead and do that. At 3 millimeters now, let's try and cut the material in half. We know we can potentially do that. So just by cutting the material in half, the cost just went down 45%. And we know that because the cost was 80-something percent. The majority of the cost came from the material. So 1.5 millimeters, okay, well, it's a cover. We can probably jump that down even further. What's 1 millimeter give us for material? So our skirt's down to $31 now, just by modifying the material and by setting it through the costing. The one thing we have in 14 is that we can actually set the material right from the model, or right from costing. Okay? The model thickness is still going to stay the same, but now we can actually set the properties here. So if we make it out of stainless, guess what? It jumps up to $340, okay, at 3 millimeters. If we make it out of 1 millimeter, it's still $117, okay? And that's because material cost in here updates automatically from the templates it's driven from. All right, so we'll set that back down to plain carbon, make it 1 millimeter, and we're back down to that $31 again. All right. So let's take a look back at the assembly again. Now, remember I said about the model or the assembly, the models will update automatically. If I click on this shelf here, get it in my tree, I'm going to change the height of the shelf. So right now it's at 12 inches. And let's just add some more inches. So it's an 18-inch difference between the two, or 6-inch. All right, so that's giving me an error because the hole in the back doesn't intersect it, which is fine. I'm not going to cry about that right now. But you can see now, my model went, let me just get off the costing because it's going to try and do that. If I double click here, make this 300 again, or 304.8 at 12 inches, and update it. Notice how the shelf grows again, or the skirt cover grows. If I increase it again, and let's just add 6 inches again, rebuild it, ignore the errors, because I know that's expected. The height of our part now changes, because that's how it was constrained in the original sketch. If we go back to it, and the hole, I'm just going to suppress it. I'm automatically going to update it, or I'm going to click on here to update it. So changing the height of it from our baseline cost increased or decreased the cost of the part by 67%. Our last one was $31, and now it's $25. Okay? So we just saved $6. So we increased the part, or decreased the height of it 6 inches. So it's about $1 an inch that we just saved here. All right, the same thing again. We can always run through, try different sizes to see what we have. Probably 1.5. So what's that? 16 gauge material? Yeah, 16 gauge. Gives us about $34 cost. So we get the strength from it, the material, and the cost is well below what we want to maintain. All right, so we went through the scenarios, saw how fast we can update changes with material, what it does to our cost. Let's go ahead and look at the PowerPoint again. Went through those what if scenarios. If I start out at 1.5 material, if I dump it down to 1.3 or 1.2, 1 millimeter, 0.9, what does that do to the cost? Using the costing, we can quickly see what the difference was in material. And we just saw it was about $1 per inch is what we saved as well. So we're going to make a final design change. So sales and marketing wanted a logo added. So we're going to update the cost again. We're going to try and, again, stay within that $50 target. Then we're going to see if we can finally do that or not with the additional request. My part here, I'm just going to go ahead, create a sketch on it. I go to Tools, Blocks, and I already have a logo here selected. So let me just go ahead and pull it up. And pick you and dump my logo on. And I'm not going to be too concerned with placing it right now. Let me just explode that so I can see what it looks like. I'm going to extrude it, or cut it. Cool. If I look at it from the front, yeah, it looks pretty. Actually, let me reselect those. There's my cut through the part. You notice it's saying click to update, so I'm going to go ahead and click it. It's going to update. And right now my part's at $263. That's because this changed from plain carbon to stainless. And it's at 3 millimeters. So the default thickness at 3 millimeters, the part with the cutout is $62. Let me dump it back down to 1.5. So $35. It's not that far off from where we were originally. Okay, so yes, we can add the cutout. No problem. It's not going to affect the cost that much. And we're even $15 under what the target was. So sales will like us even more. And take a look. Now, let's go back to the assembly. All right, so there's our finished product with the logo. We increased the shelf distance here. We saw how our part updated accordingly as well. Okay. So having said that, go ahead and take a look at what's new with 14 in sheet metal. And I'm going to go over these real briefly because we have the what's new at the end, next presentation, that will go over all this in more depth. But in sheet metal, we have some enhancements to swept flanges. We have cylindrical and conicals now. There's a new gusset feature, which is this one down here. So lengthening ribs, gussets within or going over a bend line, they were kind of tricky, or you couldn't do them prior to 13. When 13 came out, we had the option to ignore that one feature to be able to flatten our part. Now, 2014, we can put the gusset in and flatten it as well. There's a new corner relief feature, and there's some enhancements to lofts as well. Okay. So, what's new with costing? Well, there's a volume costing option now. So instead of, in the machining side, taking the entire finished part and recognizing it, we can actually take the volume of it and try and figure out a cost that way. We can set up machine-specific cost templates. Okay, so if you have a certain machine that does one certain operation with a certain cost separate from our other machines, we can set that up. We have a limited access option. So in other words, we send a part out to a vendor, that cost option or data won't be over there and they won't have access to it. With sheet metal, we can, like we saw already, we can do a scrap percentage. We can use a machining template on some costs, and we can set the material in SolidWorks or in costing to SolidWorks. We can convert circular cut paths to holes. It's like we saw earlier with that hole I put in with the hole wizard. It automatically got put in as a cut path. We can actually change that to a hole within the costing module so it calculates correctly. So having said that, that is the end of the presentation. I'm sure you have questions. If you do, feel free to email me, give me a call, or call the general support line as well. Either way, like I said, you have questions, let us know. We're here to help you. All right. Thank you and have a good day.